Okay, welcome to the second part. Here I'm going to show you how you connect the parts together and how you create the joints such that, for example, this arm here can rotate around this axis here. If you're interested in the GUI, just go to the third and last part of this tutorial series. So let me start with playing the simulation again. So in the last video at the end we have seen that everything is falling apart. So I have the Newton solver selected here. So hit play. Okay, it's falling apart, and first we would like to define our static objects. That would be in our case the tower and the base. So let's hit stop. And what I'm gonna do is I'm gonna double click on this cube here, double click, then you will see the scene object properties appear. I will leave this window open throughout the whole video. Just place it somewhere that it doesn't confuse you. And then down here you see dynamic properties, so hit this show dynamic properties dialog. Also this one I won't close it, but I'm moving it somewhere over here. And you see body is responsible. That's fine. That means other objects can collide with the body. That's okay. But we don't want this body to be dynamic, so uncheck this one. Okay. And now simply select the tower, and same goes for the tower. We don't want this body to be dynamic. Okay, let's see if that works. So hit play, and you see the tower and the base have become static. Let's start by connecting the arm to the tower. So what we really want is that this arm here will rotate around the z-axis of the tower. So if I click here, you see the x-axis, the y-axis, and the z-axis will point in this direction, which will be our desired axis of rotation. So just go ahead and right click, add. Now we go to joint, and for this one, to make this rotation possible, we need a revolute joint. Hit this one, and it's very small, so let me change the size of this. Let's go for 0.3 and diameter 0.6. Okay, let's go ahead and move this a little bit roughly to the correct spot. Let's say we want it somewhere, it doesn't matter, let's place it somewhere here. And if you really want to exactly align this revolute joint to the tower, what you can do is you select the object you want to align, and then press shift on your keyboard and select the reference. So our reference is the tower, and then you can go over here to position, and it will show you the position of the tower. And you want this revolute joint to have, let's say for simplicity, have the exact same position. So if I hit here, you'll see it moved it down here, of course, since this is the reference frame. So now it's nicely aligned in X, Y, and Z. So let's only move this along Z somewhere somewhere reasonable. Let's say, oops, along Z somewhere here. It doesn't matter, okay? You could have left this joint here, would work fine, but I like to have the joint where they physically really are, okay? So if you hit play, you will see it's still falling apart since we have not yet specified what is the connection. So let's go over here and first rename this one. Let's say this is our arm actuator. What is it doing? It is connecting the tower, so drag and drop this arm actuator into the tower. connecting the tower with the arm, right? So simply drag and drop the arm in the arm actuator, and that made the connection. See, it's connected. Now to really show you that it's able to rotate around this axis, let me select this arm actuator, and then you go again in the scene object properties. I mean, if you closed it, you would double click on this item here, then you will see the scene object properties. Here again, dynamic properties, show dynamic properties dialog, hit this one. Okay, it will be a different one for the joints, and you see this property motor enabled. And of course we would like to have this arm being motor enabled, since there will be a motor that makes the arm rotate. Okay, let's say target velocity, let's test this with 10 degrees per second. Let me show you what happens if you don't change this maximum torque. So here we got a really big arm and 2.5 Newton meters. It's not a really high torque. So let's hit play, and you see nothing happens. What happens if we say, oh, I want this to have 5,000 Newton meters, and you'll see the arm will start rotating since it has enough power to rotate the arm. Let's say minus 10 degrees. Okay, that seems to work. 0. Okay, it works. Now before I move on with the joints, let's look at how we attach this counterweight, which is not moving. What you could do is you add a prismatic joint and just give them 0 velocity and fix it. But I'm showing you another way how you could simply connect two bodies with each other. We go ahead, add. This is a little bit strange, but you can use a force sensor. So let's move this. Let me take this down here. Let's move this along X and Z, somewhere around here. I mean, it doesn't matter where you place the force sensor as long as you're not interested in the forces, especially in the torques. So let's place this force sensor into the arm, and what is attached to the force sensor? It's the counterweight. Let's hit play again. You see, it's attached to the tower. And okay. Okay. Now our next object, right click, add joint. This will be a prismatic joint. A prismatic joint allows translations in one axis. This is what we want for the crab, right? So let's go ahead and move this along X and Z, somewhere here. Let's make this a little bit bigger. 5. It's okay. So now the Z-axis is pointing up, so this prismatic joint would allow a linear movement, or a movement in the Z-axis, but we want the movement to be in the X-axis, right? So let's go ahead and rotate this prismatic joint 19 degrees in the Y-axis, right? The Y-axis is pointing in this direction, so let's rotate it 90 degrees in Y. Go over here to object item rotate. We would like to have a rotation. Now it's important that you select, you want to rotate it in the own frame, so select own frame, and you want to have 90 degrees in Y. Okay, see, that's it. Now let's align this prismatic joint nicely in the Z direction, such that it has the same coordinate. It's not important, but it's just for it looks a little neater. So select the prismatic joint, hit Shift on your keyboard, right click. Now we would like to have a translation again, position, and here we would like to have the same Z coordinate, right? Okay, that looks fine. Let's give this a name. This will be the crab actuator. Come on. Okay, and the crab actuator is sitting on the arm, so let's drag and drop this into the arm, and then what is attached to the crab actuator? Of course it's the crab. Okay, now select this crab actuator again, and you'll see here motor joint dynamic properties. So again, if you have if you don't have this window, if you closed it, double click here, you will see in Scene Object Properties, Show Dynamic Properties dialog. Here you go. So here, motor enabled. Okay, and the same goes for this one. So let's say the maximum force is 1 kilonewton, 1 E3. Okay, lock motor when target velocity is 0. That's fine. Let's test it with 1 meters per second. Hit play. Okay, it worked, but you see it only did a small distance. Why is that? Thing is, before you add an actuator, you should always first specify the configuration. So it means, you know, what is the minimum position? Let's say minimum is 0. What is the position we have drawn the crab? So I like to move this crab. Let's go ahead, mouse translation along X. Let's move it to the start position of the crab, so the crab can't go any further in negative X. Let's say this is our 0 position, and we really, before we connect anything, we need to tell them, okay, the position of the object we would like to add is really at 0. If you have something else, you plug in the number, but this is easier. Okay, and now what is the range? So now the range here is 1 meter, which means this crab is only allowed to go 1 meter, but we would like to make it more than 1 meter. So how do we find out this this length? I mean, if you have a drawing, you could measure it, but I pick this, move it along X, and you see on the right there is a plus 0, 0, 0, 0, which is the translation. And you see now we are at 6.5, which is totally fine. So our range will be 6.5. Let me undo this. So let's go ahead here and say the range is 6.5. Now let's hit play again. Of course I didn't connect it. Arm, crab. Okay, start. Now it should stop somewhere around here. Okay, looks nice. Okay. Okay, to model the steel cable, you could think, okay, why not simply add another prismatic joint to the crab that connects the mast to the crab, and you're done. You may think you could do it in this way. Let's do it in this way and see what's the problem. Prismatic joint, let's give it the name. Let's say this is our hoist actuator. This one is again pretty small, so let's go for 0.5 and 0.05 just for simplicity. Now let us align this again with the crab. I would like to have this at an end position. Let's move it somewhere here. Okay. Now let's say the mass is not supposed to go any further down. I mean, it doesn't matter, but let's suppose this. So what is the way the mass can make? Let's say the mass can go up, yeah, let's say 5.3. It doesn't matter. I mean, I will just show you how things work. What did we say? 5.3. So let's say the minimum position is minus 5.3. We have drawn the mass to be at the minimum position, so minus 5.3. What is the range? It's 5.3. Okay, so this goes from minus 5.3 to 0. Okay, now we can connect this hoist actuator, and let's make it the wrong way. So we directly attach this to the crab, and then let's go ahead and take the mass into the hoist actuator, and let's see what happens. You see, I mean, it's connected and it's nicely moving, but we don't have this swinging behavior. That is because these prismatic joints only allow a movement in this direction. Okay, so there is no way that this mass can swing. Okay, no way. So therefore we introduced this hoist actuator, this upper guide, I'm sorry. And what we will do is we will connect the hoist actuator to the upper guide. And then we need some connection between those two, such that this rotation is possible. To do this, we like to add joint, and this is the last one, is a spherical joint. This makes all the motions possible here, and I will not rename it, and it will be a helper. We won't use it, it's not actuated. Let's place this between the crab and the upper guide, and let's align the spherical joint and the hoist actuator properly with the crab. So position, tuck, okay, nicely aligned. And let's move this spherical joint into the crab and the upper guide into the spherical joint, and see again what happens. See, now we have this desired behavior of a swinging mass. Let's have this hoist actuator to be motor enabled. I'm giving it the torque of 6,000 Newton. Let's see if it works. 1 meter per second. Nice. It works, and it stops at the expected position. -1. Okay, that looks reasonable. Let's remove these velocities, and I mean, you're done. That's it. That's the linking. And you see, it's very annoying to control these speeds. You know, you always have, okay, crap, I don't want this to have 0, but maybe -1. Oh no, I would like to have it 0. I mean, it's not very nice. So therefore you would like to have a speed control where you can easily modify the joint speeds.